Welcome everyone. Our second speaker for today's seminar is Xuhui Zhou. He is a PhD candidate in the Department of Aerospace and Ocean Engineering at Virginia Tech under the supervision of Professor Heng Xiao. He obtained his bachelor and master's degree from Beihang University before joining Virginia Tech in 2020. His research focused on data-driven turbulence modeling with an emphasis on data simulation and machine learning. Xuhui, with this small introduction, thank you so much for joining us, and the floor is yours. Whenever you're ready, you can start.
Oh, okay. Thank you. Thank you for the introduction. Okay, so actually I changed the title a little bit. So actually the original title is Learning Non-Local Constitutive Models with Neural Networks. But yesterday I think the turbulence model is more accurate because we're talking about the fluid mechanics. So okay, first I would like to thank Professor Karidakis for the invitation. And the title of today's presentation is Learning Non-Local Turbulence Models with Neural Networks. And today's presentation, okay, hear me?
Yes.
Okay, and today's presentation is divided into 5 parts. First, the introduction of background of the turbulence modeling with the Rand's equations. And the second section is actually we want to use the convolutional neural network for developing the non-local models. But soon we realized that the convolutional neural network has some limitations. So we developed the vector cloud neural network for developing the non-local models. First, we aim for the scalar closure and then transit to the tensorial closure. And finally is the conclusion. Okay, so for the introduction, before this, I would like to thank my collaborators. So the work presented here was performed under the supervision of my advisor, Professor Heng Xiao, who has recently moved to Germany, and Dr. Jie Chunhan from Philatelian Institute. Okay, so as we all know, the turbulence is ubiquitous in the many natural and industrial flows. And we can see from these examples from the ocean waves to the aircraft engineering and the subflow over submarine, and we see many turbulent flows. And for simulating these turbulent flows, the Reynolds average Navier-Stokes equations are still the most commonly used tools for the industrial applications. And although currently we have more computational resources and we have developed so many high fidelity methods like the LES and the DNS, but they are still too expensive for the routine use and for the practical flows. However, the drawback, the limitation of Rand's is very obvious. They have poor performance in the flows with separation or flows with strong curvature. So for this simulation, for the Rand's equations, we need to quantify and reduce the modal uncertainty in the Rand's equations. Okay, let's see what is the Rand's equations and where is the source of the modal uncertainty. So this is the incompressible Navier-Stokes equations. I think many of you are familiar with. And if we are only interested in the mean flow behavior, we will do the Reynolds decomposition. We decompose the velocity and pressure into the mean part and the fluctuating part. And in this way, we can rewrite the Navier-Stokes equations and we get the Reynolds average Navier-Stokes equations. However, we can see there is one more term on the right-hand side of the momentum equation. And this term is known as the Reynolds stress term because there is no good solution to approximate or to model this term. So we say that the Reynolds stress is the source of modal uncertainty in the Rand's equations. And how can we model it? The most commonly used method is the linear eddy viscosity models, which is shown on the brown box, the eddy viscosity models. And these types of models are based on 2 assumptions. The first one is the Bushnig's assumptions, and which says that the derivative part of the Reynolds stress tensor is locally dependent on the mean strain rate at the same point. And we can also see this on this in this brown box, the first equation. In the small yellow box, we can see this is the anisotropy part or the rhetoric part of the Reynolds stress. And on the right-hand side, we can see 2 newTs. So which means the anisotropy part of the Reynolds stress is proportional to the mean strain rate at the local point. And because of this, it is insensitive to the secondary flows and the strong flow with strong curvature and rotation. And the second assumption is the weak equilibrium assumption. And this assumption says that only the variations in the turbulent kinetic energy is accounted for and with the transport equations. Now, however, the anisotropy part of the Reynolds stress is neglected. We can also see from the first box, we can see there is only one transport and equations in this box. That is for the turbulent kinetic energy. But for the anisotropy tensor, there's no transport equations for that. And there are also some other models for modeling the Reynolds stress. However, as we mentioned, the linear eddy viscosity models has their limitations. It is good for the equilibrium flow. However, for the non-equilibrium turbulent flows, and we really need a non-local model such as the Reynolds stress transport models. As we can see from this equation, this transport PD directly model the Reynolds stress, and it implies a non-local mapping. And according to the NASA 2013 report, the Reynolds stress transport model is the golden standard in the next few decades. And however, the Reynolds stress transport model has their own limitations.
Xuhui, sorry, I have a question. How do these pictures show the non-locality that you're talking about? Can you be a little more specific? You're saying from here we need fully non-local models. How do I see that? Okay,
so can you see the right figure? So the right figure means that if we want to predict the Reynolds stress anisotropy at, for example, at a point, which is represented by a blue box, and it is non-locally depend on the mean velocity field in the surrounding neighborhood.
I see. So it's not the whole domain, it's some cut out region around it.
Yes, if it's depend on the whole domain, then I think it's computationally expensive. So the typical way is that we account for some a very non-local. For example, we model the mu t using the transport equations over the whole domain. But if we consider the anisotropy part, we think it is proportional to the local strain rate.
Also, can you define for me a non-locality? Because I work on fractional modeling. But what do you mean by non-locality here?
Okay, so let me go back to to these slides. We can see that if we want to accurately describe the motion of Reynolds stress tensor, then we should directly build a transport equations for the Reynolds stress tensor. And however, the traditional method like the eddy viscosity models here, it assumes that the Reynolds stress anisotropy is proportional to the local mean strain rate S. That is the local relation, but the non-local part, the
no, I understand
yes,
this.
Yes.
I'm looking for technical definition of non-locality, but so here you mean spatial non-locality?
Yes, spatial, yes.
And you're looking at URAN, so you have time dependence. So you could also have memory term.
Yes, but now we are considered the steady state Reynolds equations.
Okay, because here you have the unsteady. You showed the unsteady equation.
Yeah, sorry about that, about the confusion.
Okay, so we're talking about spatial non-locality.
Spatial, yes, spatial. Yeah.
Which you truncate somehow around the point. Instead of just the point, you take a neighborhood of that point.
Yes, yeah.
Okay. Thank you.
Okay. So our aim is that can we devise a non-local neural network-based model for the Reynolds stress anisotropy because we want to capture the transport of the anisotropy due to the convection and the diffusion. So here we can see from the right figure, if we want to predict the Reynolds stress anisotropy at the point, we want to build a mapping from the mean velocity field in a non-local region. Okay, so initially we want to use the convolutional neural network for building these non-local models. And the motivation is from here. And we consider a steady state transport PDN with the convection, diffusion, and the production term for a tracer. And we can think of like a concentration. This is analogous to the Reynolds stress tensor. And here the production term is locally depends on the velocity and the concentration, and the E contains the dissipation term and any source that are non-local functions of velocity and concentration. And if this transport PD is nonlinear, is linear in the concentration, then we can derive the formal solution in a convolutional structure. So we can see the concentration at a point is a convolution of the Green's function G and the production P. So to represent this convolution, I think the convolutional neural network is a natural choice. So we want to build a mapping from the mean velocity field in a non-local region to the trace at the central point. And how can we do that? And we are inspired by the solution structure. We can see from the right figure, we have the velocity field in a non-local region. And there are two branches. On the upper branch, we want to use a convolutional neural network to model the Green's function G. And on the branch below, and we can derive a strain rate and the rotation rate field directly or compute it directly from the velocity field. And then we use a fully connected neural network to model the production term P. And here, each point in this strain rate and rotation rate field shares the same network because we think the production is locally dependent on the mean velocity field. And after we get the Green's kernel G and the production, we do the convolution to get the prediction. Okay, so in first case, we want to verify the correctness of our method. So we want to make sure that we are actually learning the Green's function, the Green's kernel. So we consider the convection diffusion equation like this, where the velocity field is a uniform field. And here the production, we assume the production is not a function of the velocity field, but is randomly drawn from a Gaussian process with the zero mean and with this covariance function. And here the dissipation term is a linear term. And in this specific case, the Green's kernel can be...
how did you come up with this kernel? I used this kernel before for ocean modeling, but I was wondering, why did you use this periodic kernel in the argument?
So this is for the periodic boundary conditions, and I'm thinking of using this is because I think if I'm using this, I can more easily handle the convolutional, because you can see there's a padding part in the convolutional neural network, and if I'm using these periodic boundary conditions, I'm more easily handle that padding process.
Because we use exactly this kernel, actually. I thought nobody had used it before for ocean modeling for the temperature in the ocean because of the seasonal variations. But so anyway, it's a good kernel. But I'm not. Yeah. So here it's because of the we did it in time. You do it because you have a periodic domain, right?
Yes. Yeah.
Okay.
The production field is periodic.
And LP is the size of the domain.
Yes. LP, I'm not sure. I cannot remember exactly, but
or 2LP or something like that.
Maybe something like that. Yes.
Okay. Right. Yeah. And what is L? What is L then? There's LP and there's L.
The length scale. I think the LP is to control the porosity, and for areas the length scale, I think.
Yeah, LP should be the domain because it has to do with the periodicity, and then L, little l in the denominator, it's how you control the scales that you introduce through the GP. Yeah. Okay. Okay.
Okay.
Please proceed.
Thank you. Yeah. Okay, and in this specific case, we can derive the Green's kernel analytically, and it can be interpreted as the inverse of the finite approximation of the differential operator here, and we can derive it and we can visualize it. So that is the reason we want to formulate the convection diffusion equation in this way. Okay, so before we looking at the learned kernel, we actually want to learn the regional to point mapping. So here we can see from the right figure, we want to learn the mapping from two fields, the velocity field and the production field, to the concentration at a point. And we generate training and test the data by varying the velocity, the uniform velocity field and the production field, and we solve the equations, we get the concentration field, and we train with some case and test on different case. And from the left figure, we compare the predicted concentration in the test case with the corresponding ground truth, and we can see the prediction is quite close to the ground truth. And on the right, we see a specific case. We compare the ground truth of the concentration with the predicted concentration. We can see the pattern looks similar, and we also compare the concentrations along two cross sections, which is shown on the bottom. The red curve represent the predictions, and the black curve represent the ground truth. We can see they're reasonably well. And the background, the gray dot curve, is represent the production term. And then after training, we can also visualize the learned kernel. As we mentioned, we can derive the Green's kernel because of the linear PD in the concentration. And here we compare the learned kernel G with the analytical kernel G. We can see the trend looks very similar, and we compare it in three different cases with different velocity field. And the x-axis means the relative coordinates to the point of interest, and the y-axis is the weight of each point. And we can see that if the point is exactly at the point of interest, that we can see it has the highest weight. And if the relative coordinates is active, that means the upstream, we can see the upstream and has contribute more to the point of interest because of the convection. And in this way, we are ensured that our method are learning the Green's kernel as we desire. And then we find another advantage of this model is that, and we can also learn the submodels of the production, and we also consider the same convection and diffusion equations. But here, the production is not randomly drawn from Gaussian process. Here, we assume it is a function of the flow field. We assume Q is a function of the strain rate as the magnitude of strain rate and the magnitude of the rotation rate. So the question is that, and can we learn the production model, the P model, correctly? And here, we can see from this figure, the production is not randomly generated. Is a function of is a local function of the S and omega. Okay, similarly, we consider the Telegreen vortex as the flow field. We verify the velocity field, and we solve the equations. And after training, we can visualize the production term, which is shown on the bottom. We can see that the production term is a composite function of Fs and G omega, and we can see after training we can learn this composite function reasonably good well. And the most important is that we learn these submodels without using data from that level. We only use the input data of velocity field and output data of concentration. We have no data for the production. But soon we realized that the convolutional neural network has some limitations. The first one is it lacked frame independence. It has the translation invariance. However, it does not have the rotation invariance. So in this way, if we rotate the coordinate system, then it cannot get the same prediction. That means the CNN has very poor extrapolation capability. And also, in many cases, the CNN requires Cartesian mesh. Although we can translate the unstructured mesh into the structured mesh or Cartesian mesh sometimes, but it is not that straightforward. And in many industrial applications, the mesh are unstructured mesh for the finite volume or finite element solvers. And finally is that for the wall-bounded flows, actually for this convolutional neural network, there are some technical limitations because for these flows, we don't know how to handle it for the wall.
How about the 3D? The 3D is not a limitation?
Yeah, it's a limitation, yes. Yes, because yeah, they're very computationally expensive.
I mean, there are 3D CNNs, but no,
yeah. So here we need a more flexible and frame independent mapping to emulate the Reynolds stress transport models. So we developed a model named the vector cloud neural network. And first we aim for scalar closure. So as we mentioned before, we want to find a mapping from a non-local region here. We represent this non-local region as a cloud, from this cloud to the cloud center. And we can see from the figure below, the cloud is represented by randomly selected endpoints within this cloud, which is marked blue. And for each point, there is a feature vector Q attached to it. And our prediction is the closure term at the red point. And in this way, the cloud is represented by a collection of these feature vectors from Q1 to Qn. And however, for these mappings, it is not straightforward because there are some physical requirements on these mappings. The first two are Gaussian invariance and the translation invariance. And these two are easy to satisfy because if we use the relative velocity or relative coordinates to the point of interest, the red point, then we can satisfy these two invariants. However, there are another two invariants, the rotation invariance and the permutation invariance, which is not that straightforward. Okay, so and how can we achieve the rotation invariance? Here we consider only use the pairwise inner product of the feature vectors, because we know that the inner product of two vectors is a scalar, which is frame independent. So in this way, we do the Q transpose, we get the D prime. And here the D prime matrix is a rotational invariant feature matrix. However, we can easily find that this D prime matrix lacks the permutation invariance. Okay, so now how to achieve the permutation invariance? We first want to introduce the very simple concept of permutation invariant function. Here I give you a few examples. The first three examples are permutation invariant functions because if we reorder or change the order of the input elements, we get the same output. But for the last one, if we change the order of x1 and x2, then the output changes. So how can we represent an arbitrary permutation invariant function? So at the very initial stage, the idea is that, and we can first construct a nonlinear function from the mean. It consists of two steps, and we first take the average of all inputs, and then we design construct a general nonlinear mapping which can be arbitrarily complicated for these average values. This method is quite straightforward because there is no intermember interactions and other than average. And in this way, we guarantee the permutation invariance. However, the question is that, is this method capable of expressing any permutation invariant functions? And later we find a more general idea is that, and we can first apply the nonlinear mapping before the averaging. And this method has 3 steps. The first is embedding, and we can first apply a general nonlinear mapping for the input. And this general nonlinear mapping can have a number of sub nonlinear mappings, for example. And here we show from the phi1, phi2, and others. And we apply these nonlinear mappings to each point, input point, equally. And after that, and we do the average for this embeddings. We get the average embeddings. And finally, and we can construct a general nonlinear mapping and for these average values. And in this way, we can get a more a universal approximation. And according to this universal approximation theory of these metric functions, we can it shows that any permutation invariant functions can be represented with this structure, and first embedding, and then averaging, and finally the fitting procedure. Okay, here are 2 examples for using this structure. The first one is with 2 inputs, Q1 and Q2. And if we define the embedding functions, the phi function as this, and the fitting functions, the psi, and in this way, and we can get these permutation invariant functions as desired. And similarly, the second example with 3 inputs, and we can also define the small the embedding function and the fitting functions. We can get the desired function. Okay, so inspired by this, we introduce a set of M functions to the scalar part of the feature vectors. And in this way, and we embed the scalar part of each feature vectors. And this we have the embedding functions, which can be think of the phi act on the CI. And we can think of this as a weight matrix on this input matrix Q. And then we do the average. In this way, we remove the influence of the index I, which is the index of each point within the cloud. And in this way, we have the L matrix. The L matrix has the permutation invariance. And also, as we introduced just now, and we can do the LL transpose to get a rotational invariance. So here, and we have the D matrix, which is LL transpose, which has all the invariance properties as we desired, the Gaussian and translation invariance, the rotation invariance, and the permutation invariance. And also, this method adapts to different number of input points, which is known as the property of a neural operator. So we can see from this figure, we first have the cloud, and which have n selected point to represent it. And for each point, we have a feature vector attached to it. We take the scalar part of the feature vector and use embedding functions to embed this scalar part. And then we also have the cloud Q, which is shown on the bottom, and we do the pairwise inner product to get the D prime matrix, and which is rotational invariant. And then we use the invariant, the permutation invariant, get the permutation invariant functions by project this D prime matrix onto this embedding matrix, and we get the matrix D, which has all the invariance properties as desired. And finally, we fit this D matrix into a fitting network to get our closure term. Okay, let's go through the whole process of the vector cloud neural network. First, is the problem statement. And we have the flow field. We want to predict the closure term or closure variable at a point. So the traditional method is a traditional PDE-based method. If we consider the Reynolds stress transport model, it has many limitations, but now we want to build a neural network-based model to augment the traditional method. We can first determine a non-local region around this point and randomly selected endpoint with this cloud. And in this way, we can have the input matrix of the cloud. We can see from this cloud Q, which has n rows, which means n different points. And each column is a feature on this point. And then we take the scalar part from this input matrix and feed it into the embedding network to get in the embedding matrix. And after we get the embedding matrix, we can get the we can use the input matrix and the embedding matrix to get the invariant matrix D, which has all the invariants as we desired, and we fed it into a fitting network to predict the closure term.
Can you say something about the size of the cloud of that region?
Yeah, I will talk about it. Yes, I will talk about
okay.
it.
Okay, yeah. Okay.
Okay, so to verify our method, we need to generate the training data from simulations. Here we consider flow over periodic here, and which is a very classic benchmark data set for turbulence modeling. And here we freeze the velocity field, and we can first obtain it from solving a laminar flow, and then we fix the velocity field, and then we solve this transport and the PDEs with this and the frozen velocity to get the concentration C or tau here. And here we formulate these transport equations by mimic the style in many turbulence models for the production term, for the dissipation term. And we do the simulations over a family of periodic here flows to generate the training data. The problem is that, as Professor Kalidakis mentioned just now, how can we determine the cloud size? So here we consider a 1D convection diffusion reaction equation here, which is a linear PD in the concentration. And for this linear PD, and we can derive cloud size by given a truncation error, epsilon, here. And in this way, we can see the cloud size error is depend on the velocity, magnitude, and also the diffusion coefficient, and also the truncation error. And we can see from this figure, the non-local region is actually elliptical region, and it aligns with the velocity at the red point. And the long axis can be determined by using the derived cloud size L, as shown in the red. And for the short axis, because we only consider in the direction perpendicular to the velocity, we think there's only diffusion, and the velocity in this direction is 0. So we set the velocity as 0, and we can also use this red equation to derive the short axis. And in this way, we determine the non-local region around the point of interest, and then we randomly selected points within this cloud as the input points. So here, here shows our training and test results. And we train and test on a family of periodic hairs with different slope parameter. The smaller slope parameter means a very sharp and hair, and a large slope parameter means a very flat hair. And we train it with the slope alpha between 1 and 2, as shown on this figure. The background is yellow. We train the train cases between this range, and we test it from 0.5 to the 4. And we also add a very different case, which is a very short case, which means the slope parameter is 0, is the backward and the facing step in the case. Okay, we train we select on a few training flows, and we train it. And after training, we test it on so many testing flows. But the difference is that for training, we fixed the number of points in the cloud. We set it as 115 points. But for testing, and we use all the points within this cloud. And because of the property of neural operators, it adapts to the different number of input points. And this point for each cloud is different from locations to locations. And we can see the prediction error in this figure is reasonably good. For the similar shapes, the prediction errors are below 3%. And for a very different shape, the slope parameter of 0 is also below 5%. And also, let's look at the predicted concentration in the two extreme extrapolated case with the slope parameter of 0.5 and 4. And we can see the predicted concentration agrees very well with the ground truth. Okay, let's then look at some physical interpretation of our design. As we mentioned before, we use the embedding network to formulate an embedding matrix, which can be viewed as a weight matrix for each point. So here, if we compress our embedding matrix into one column, then we can directly visualize the weight for each point in the cloud. And we do it in this way, and we can see the weight contour in 5 different locations. And the M means the cloud in the middle in the middle channel. And there are 2 in the recirculation region, and there are 2 on the wall. And we can see the weight contour in this near this point. And this is more clearly showed in this slide. We can see for the medium channel, the upstream flow has higher weights than the downstream. And this is also clearly shown on this figure C. And we plot the weights along the velocity directions. And for clear visualization, we reflect the weights on the upstream to the downstream with a dot line, with a dot curve. And we can see for the red curve, the upstream has more weights than the downstream. But for the recirculation region, we can also see from above, there are 2 red arrow, and which is more shorter than the red arrow in the M circle, and this represents the magnitude of the velocity. And we can see in the recirculation region, the magnitude of velocity is very small. So the weights in upstream and downstream is not that clear, but we can also see from the figure below, the figure C. The weights in the upstream is slightly bigger than the weights in the downstream. And also, we can see the weights near the wall. If we plot the weights along the direction that is perpendicular to the velocity direction, we can see the black curve and the gray curve. And when the relative coordinates is 0, that means the exactly point at the wall has the greatest influence. But if it gets far, then the influence of the weights of the weights decrease. Okay. And so far, we only consider the modeling for a scalar enclosure that will not change with the rotation of the coordinate system. But many physical laws are covariant, which means the output covariance or co-rotates with the coordinate system. And here the example shows the rotational invariance. The rate of energy loss is proportional to the velocity magnitude. If we rotate the coordinate system, the velocity will also co-rotate, but the magnitude remains the same, and the energy loss keeps the same. However, in many other cases, for example, in the Newton's second law and for the viscous stress of Newtonian flows, it's the rotational covariance. If we co-rotate the coordinate system, then the acceleration vector and the force vector also correlate in the same way. And this is similar for the viscous stress of Newtonian flows. And for this case, unless we mathematically guaranteed by the formulation and the neural network design, the network has no way to know the connection between the input and output. And if there's no design, then we cannot guarantee that the output can correlate with the coordinate system. So we need to design a neural network that can ensure these asymmetries. And this is a hard constraint or hard requirements needed for so many physical laws and constitutive relations. And so here, we equip the vector cloud neural network with the equivariance or covariance. We can see this figure. The design is very similar to the vector cloud neural network, but the difference is that after the fitting network, we do not directly predict the scalar closures. Instead, we first output a series of scalars to construct an invariant diagonal matrix, and then we can rotate this diagonal matrix with the x theta, which embeds the rotation information. The x theta here we can see is the first 3 columns of the G transpose Q, which has the rotation information. And in this way, we guarantee that our predicted Reynolds stress tensor can correlate with the coordinate system. Okay, to emulate the velocity to Reynolds stress mapping, we generate and organize a DNS database for flow over 29 from parameterized periodic hairs, and this data set has been shared on the NASA turbulence modeling on the website. And we take 7 flows from there. We train on the 6 and test on the 1, which is bounded by the green box. And we train on the 6th flow and test on that one. We can see the predicted Reynolds stress component in that testing flow compares well to the ground truth. Here we can see the result. We have 4 columns, which means the 4 Reynolds stress components. And we can see the predictions are quite close to the DNS data. And also, we compare our method with the classic linear at viscosity models. So, okay, in the first row, that is the prediction error of our method compared to the DNS data. And on the second row, that is the traditional method. And we can see that in the recirculation region and in the contraction region above the here, the error from traditional method is much higher than us. And finally is the conclusion. And in this work, we explore the feasibility of using non-local informations, and which has the potential to complete the local models and improve the anisotropy predictions. At the initial stage, we tried using the convolutional neural network to emulate the non-local mappings inspired by the formal solution structure of convolution. And then we realized there are some limitations in using the convolutional neural network. And we developed the vector cloud neural network for the scalar closure, and then extended it to the vector cloud neural network with equivariance for the tensorial closure. And we also have some preliminary results in emulating the Reynolds stress transport PDEs that is implied by the DNS data. Okay, all right. This is my presentation, and thank you all for being here, and I'm open to any questions.
Thank you so much, Xuhui. That was a really nice talk. Do we have any questions from the audience?
Maybe Zhan has questions. He's a turbulence model expert.
Yes. Hi, Xuhui. I'm Zhen Jiang, a postdoc here, and I have a lot of questions about details. But first, I want to make sure all of the input of this model.
Okay, you mean the cloud point?
Yes, vector cloud method. So here, so we have many points, and at each point we have the positions and all the features, right?
Mm-hmm.
And I think we also need to know the domain size and also the number of points. So it is also part of the input, right?
Yeah. Yes. But here we assume the size of the cloud is derived from a very simple case, the linear transport PDs, and we derived the size, the long axis and the short axis of the elliptical non-local region. Yeah.
In this method, the input to determine the domain is the velocity, or so what is the input of the method to determine the domain using the
It's the relative velocity to the point of interest. It's actually, you can understand, actually it's like the velocity gradient.
A velocity gradient.
Because we have the distance, the direction information. We also have the relative velocity, the information, and which implies that we are actually using the velocity gradient. But if you have this kind of information, I think, and we can embed that gradient information here.
Okay. So I think it's a very interesting work. So finally, if we apply this method to every point, we actually realize some operator from a velocity field to your closure field. For example, is a viscosity, a field of viscosity, right? So I think what I want to ask is, if given a field of the velocity, given a velocity field, and given a subdomain where the point to be sampled in, and if we change the method of sampling, will the map between this velocity field to the closure field keeps the same, or it depends on your how to say?
This is this is a very good question. So we have included a figure in this paper, as you can see below the JSP paper. We have investigated the effects of number of input points, and we can see that there's a convergence process if we use more points within this input cloud, then we can get to a smaller prediction error. But as you said, the sampling method and the number of points will definitely influence the predictions. It is more like a stochastic process, but as we increase the number of points, then we can get a very close predictions.
Okay, thank you. Very interesting work. Maybe we can discuss with some detailed problem later.
Yeah, sure. I'm now in the Providence. Yeah.
Yeah.
Oh, I see. You're in Providence. By the way, the same, the last part where you work with tensor, you can use that in LES, right?
Yes, I think the method is can adapt to the RANS and LES, correct?
So in the chat, I put a paper that I wrote with Charles Menevaux, where we tried to do a priori test for a non-local fractional model using fractional derivatives. So you can see the JFM paper in the the anniversary issue for Bachelor, and we actually have what they call the Karman-Hawthorne equations. So you can, if you satisfy those equations, you know that actually you do it right. So maybe that's one way to objectively evaluate any non-local models. Are you familiar also with the models by Hamba? He has
no.
Oh, he was the first to do, basically the first guy to think about non-locality is Robert Krajnan, who's the last student of Einstein. So he wrote, for 2D scalar turbulence, he has exact solutions, and he was talking about non-locality in the 60s, actually, in the 70s. But anyway, we now with fractional models, fractional derivatives, you can do that, or temper fractional derivatives. Also, my student Mohsen Nuri has a paper on non-local closure models in JFM. But our paper basically shows that you can, it's a very rigorous test to see how accurately you satisfy these equations a priori, so you don't have to do a posteriori big simulations to check it. And there's comparison between, for homogeneous turbulence and wall turbulence between local and non-local in terms of the spectra and so on.
Mm-hmm.
In your last example, you didn't show the non-locality of the model. Did you have a picture like that in the paper?
No, I don't think so, because we've fixed the non-local region by deriving, but with the length deriving from that equation. So we do not investigate the size of the cloud.
Okay. The size and the shape.
Yes, the size of the shape.
If
But
you
I
have
think
an
it's worth doing. Yeah, it's worth doing.
Isotropic flow, even
Yeah.
the channel flow is totally anisotropic in one dimension. So those very interesting ideas, and also the equivariance. There are rigorous ways of including equivariance using on CNNs. People have done that in computer science community because of in computer vision.
Mm-hmm.
The azimuthal equivariance is important. So there are a multitude of methods, but I think your cloud method is really promising. It's just that the size of the cloud is important in
Yes, right.
special developing flows.
Yeah, I agree.
But well, stop by the lab since you're local. You should stop by and have a chat. Okay.
Okay.
Thank you, Xuhui. Do you have any other questions from the audience? If not, I think that we can close this week's seminar. Thank you so much, Augusto and Xuhui, for your time today. Those both were really nice talks, really informative. And with this, we can close this week's seminar. And so have a good weekend, and until next week.
See you.